So we are moving into the second week of the module, and the topic today is about uncertainty and the methods that we use to deal with it when we design intelligent systems. I will give an overview of a couple of techniques which are traditionally used to deal with uncertainty, and then I will focus more on fuzzy logic, which is the main method covered in this module. Next week is going to be again about fuzzy logic, how we use fuzzy logic with some practical examples for the design of fuzzy systems and fuzzy clustering. So today I'm going to start with the notion of reasoning, which is, of course, a process conducted by humans, and explain how reasoning has been used in the context of intelligent systems. And I will focus more on two approaches. One is based on probabilities, is the well-known Bayesian reasoning approach. The second one is based on the theory of certainty factors. That will be the first part, and then I will focus more on fuzzy logic, the theory of fuzzy logic, how it was introduced, some key concepts about fuzzy sets, fuzzy variables, and how we use them to design, to create fuzzy rules. So what is reasoning? Reasoning is a process, a high-level process is associated with the thinking, cognition, and intelligence in humans. It's a process that we use when we form inferences about the world. So we start from something which is believed to be true, or some hypothesis about some fact that we're making, and we combine the information and we reach a conclusion. In humans, there are roughly 4 types of reasoning, and you can see it on the slide. It's deductive reasoning, inductive reasoning, causal reasoning, and analogical reasoning. These are processes which have been studied for several decades in psychology and in other disciplines, in neurosciences, and they have influenced a lot the way artificial intelligence systems are created. In artificial intelligence systems, we try to somehow create computational models that imitate these kind of processes of deductive reasoning, inductive, causal, and analogical. So inductive, for example, is reasoning based on examples, and we use it to support certain claim. In deductive reasoning, we start from the general principle, and then we try to argue about a specific case. In analogical reasoning, we draw on previous experiences. We make comparisons between information we collect and facts, and we try to find similarities in order to reach a conclusion. So this kind of processes has influenced a lot the way machine learning and AI methods have been developed. For example, inductive reasoning, you can see it's based on examples. Most of the machine learning methods are based on this idea that you are presented with a data set, some kind of examples. These are in the form of data points, feature vectors, or images if you use deep learning. And then through the process of training, your system is able to make decisions. It's a form of inductive reasoning. Analogical reasoning has been used a lot as well. There are case-based reasoning systems. Typical example, the knowledge that the system has is represented through some cases, examples in a sense of, and the system uses these kind of examples through some use of similarity metrics in order to find similarities and find the most relevant knowledge that it has and apply it in the particular situation. I have here a link. You can click it, you can find on the slides, and you can see a video. It's about Sherlock Holmes. It's famous for his abilities to perform reasoning and combine different kind of diverse pieces of information, manage even contradicting information, and reach conclusions, solve difficult problems. In this particular video, he fails. Actually, it would be interesting for you to have a look. He tries to generalize, and unfortunately, at the end of the process, the conclusion is wrong. But still, it's an interesting example. You can see how different humans can use different types of reasoning to deal with a particular kind of situation. So what happens in AI? In AI, when we are talking about reason, it's a mechanism for selecting facts, extracting conclusions in a logical way. The logical way depends, of course, on the knowledge and how the knowledge has been represented in the system. And the reason is nothing more like than a kind of computational mechanism that receives information inputs from the facts, has already some kind of knowledge established, either in a separate knowledge base or distributed. For example, in neural networks, the knowledge is distributed in the network. And then, judging from the existing knowledge, it produces decisions. In real life, we associate the concept of probability a lot with abstraction and uncertainty when we perform reasoning in real life. So we use words like probably, likely, maybe, perhaps, possibly, and we are able to, despite the uncertainty, to make conclusions. When we are doing, when we work with intelligent systems, it's not that simple. Intelligent systems, AI systems, have difficulty understanding and giving meaning to abstract words. So everything is done through a process of transformation from abstract words, concepts, into numeric values. And when we're using probabilities for reasoning, these numeric values are between 0 and 1. This is how normally probability is represented. And as I said from the beginning, one of the basic approaches that people use in AI reasoning is Bayesian reasoning. It's based on the Bayesian rule, and you can see on the slide the rule. It uses the conditional probability. It's the probability of A happening given that B has occurred, okay? And to operate, it needs obviously some other information. It's the probability of A, the probability of B, the probability of B given A. So we have to have all these numbers, put it in the formula, calculate the result to get the conditional probability. It is possible to reformulate a bit the equations and describe the probability of A and probability of B, given information that we have about two mutually exclusive events. So B and not B, A and not A. If we have this kind of information, we can use it in the formula and we can slightly modify it in order to calculate the probability of A and B. And you can see on the slide how this works. And then we substitute it into the equation and we can get an alternative formulation for the probability of A given B, as you can see here on this slide. What is more important in practical applications is the formulation that you see here on this slide, which is an expression of Bayesian rule in terms of hypothesis and evidence. Evidence comes from there are different sorts of evidence, okay? So evidence, a piece of evidence may be supplied by the user. If you have an AI system that receives user input, then the information that the user provides can be used as evidence to trigger some hypothesis. In other situations, the evidence comes from information that we collect through different kinds of sensors of the system. So the evidence gets numeric values. It can be put into some kind of equation that can trigger a calculation for probabilities. So according to this formula, what we have is that the probability of hypothesis H being true given evidence E is given by, it depends actually on the probability of H, the probability of E given H, the probability of not being H that can be interpreted as a prior probability of hypothesis H being false, and the probability of E given H, it's not true, okay? So if we have this kind of information, then we can put in the equation, we can easily calculate the result. The problem is, of course, that in many practical applications, we don't have all this piece of information, and we have to operate under some assumptions. And one of the most normal assumptions that people make in several applications is to assume that there is conditional dependence among the different events. And this is important because it simplifies a lot the process. So the formula is, as you can see in this slide, slightly different. It's the probability of any hypothesis H, and I have here HI. I can take different forms, H1, H2, H3. These are different hypotheses that the system has to make. Can make, and the hypothesis is made subject to some pieces of evidence that are collected. These are denoted by E1, E2, En here, and the calculation is transformed into some kind of multiplications between conditional probabilities and a priori probabilities, as you can see in this formula. Still, we need some information, so we would need to know a bit how the probability of hypothesis 1, for example, is calculated. We need to have this piece of data in order to make this thing work. But the whole thing is much simpler than it was before, and this is a popular way to work to quickly design an intelligent system if the information about probability is available. I have a simple example to show you how this is going to work in a simple case where we have a system that needs to examine 3 hypotheses, H1, H2, H3. And this calculation is the calculations are based on 3 conditionally independent pieces of evidence, E1, E2, E3. Okay. The probability can be provided by an expert, by a human who has this kind of knowledge, or I don't know if you remember last time I talked about multiple experts, an approach that has used a lot introduced at the end of 80s and 90s. A lot of work about the design of multiple experts. These are different kind of AI systems, specialized experts in making decisions under particular kind of conditions. So you assume that you have some kind of knowledge. This is embedded either in the form of numbers given by experts, human experts, or produced by decision makers, which are on their own independent AI systems, and they feed your system, and your system can use this information to make decisions. So the whole knowledge that our system has is represented in this simple table in this case. Our knowledge is represented by probability values, and you can see the values in the table. There are rows for each one of the hypotheses that the system can examine. So the first one is the probability of hypothesis 1. This is 0.4. The probability of hypothesis 2, this is given as 0.35, etc. And then you have other rows which shows you conditional probabilities, the probability of E1 given H1, 0.3. The probability of E2 given H2 is 0 in this particular case. So we assume that the system has this kind of knowledge. This is the kind of knowledge that has been represented in the system, all summarized in this one table with these numbers. And we assume that the system operates and it receives from the sensor some kind of information. It observes E3. Okay, so the system needs to compute the posterior probabilities for all the hypotheses available. And you can see on this slide how the equation is transformed. So we have the probability of a hypothesis given the only piece of evidence is E3 in this case. This makes calculations simple, and you can see my calculations on this slide. So the first is to calculate the probability of H1 given E3, and in this case is 0.34. Second one, the probability of hypothesis 2 given E3, 0.34 as well. And the third one, the third hypothesis is 0.32. Practically what that means is that after evidence E3 was observed by the system belief in hypothesis H2 becomes equal to the belief in hypothesis H1. This is because the probabilities are the same. Okay, so the system will have to update its beliefs about this hypothesis, making E1, H1, and H2 equally probable. Also, we find that the belief in hypothesis H3 also increases, and actually it reaches a value which is very close to the beliefs in hypothesis H1 and H2. So this is how the first cycle, the first iteration, let's say, in the reasoning of the system. Okay, so at the moment, the process hasn't finished. We are in an intermediate stage. The system basically does not have a clue. Okay, there are two hypotheses which are equally true, and there is a third one which is very close in terms of probability value. So it would be very difficult for the system to make a decision at this stage. So we assume that the system gets an additional evidence. In this time, the evidence is E1. That will change, as you see here on the slide, the formulation of the equation because we have additional information. So in this case, we have to calculate the probability of H1 given two pieces of evidence, E1, E3, and we do the same for the other hypothesis. And what you see here is that everything now changes because H1 is now 0.19. H2 0.52 and H3 0.29. What that means is that in the second iteration, the system actually starts believing that H1 is the most likely hypothesis. What has happened so far, the information that the system has received from the environment, from its sensors, which has been represented by these two events, E1 and E3, actually now tells the system that, look, the situation has changed. Probably it's what is currently happening is H2. But we haven't finished. Let's do one more cycle. In the next cycle, we assume that A2 is observed. So the system gets more information. It remembers that it has seen E1 and E3. So all the information together, all the data together actually are E1, E2, E3. So given that we have three pieces of evidence, the system will go again through Bayesian reasoning and calculate all these probabilities. H1, H2, H3, and as you can see, the situation changes again. And what happens is that H1 now is 0.45 and H2 has become 0 and H3 has become 0.55. Normally what happens is that the system is trying to apply the max rule. So they will check the probabilities and they will pick the outcome, the hypothesis or the decision that looks more probable. So they do some kind of ranking. And although we see from the initial ranking H1, H2, H3, now it seems that only H1 and H3 are valid. H2 has become 0 based on the evidence that we have collected so far. And the most probable one is H3 because the probability is 0.55. So the system will give you as a decision H3, hypothesis 3, as being true. That's the perception of the system according to the information that was provided in the initial matrix with the probabilities and the pieces of evidence, the facts that the system has received from the external world or from the user. So this is how basically works. There are different formulations of Bayesian reasoning. This is one of the simplest that I described here. People use other ways like Bayesian networks, where we have concepts and they are related with links, and the links are associated with probabilities. But again, there is an input, the input nodes, the input constants are triggered depending on the data that are received from the environment. And then the output nodes represent the hypothesis, like in this case, and you find which one is gets the maximum value. And in general, this maximization rule applies and we calculate the output. Another idea is to use certainty factors. It's a completely different approach. Bayesian reasoning obviously is based on some strong mathematical theory, the theory of probabilities, and there are theorems. It's mathematically is considered very strong, convergence proofs, etc. Certainty factors theory, it's more heuristic, someone could say. There is no strong mathematical theory behind it, and some of the equations that I'm going to show you may look, uh, I don't know, fuzzy in a sense, but this is how they have been defined, and they have been used in applications, and they perform well. The whole idea is that we have the notion of certainty factor. That's a number that represents an expert's belief. It's not a probability. It may look like probability, but it's not really a probability. It's the belief that someone has on a particular kind of event or on a particular kind of action. Okay, and the maximum value that this belief can take is +1. It seems that we are very certain that this thing is true. Something this happening is true. And then we have the minimum value, which is -1. It's completely the opposite. What the event is, what we happening is definitely false. Okay, so if an expert is believes that something is certainly true, a value of 0.8 could be assigned to this evidence, and that value is very strong. It represents that this person, or if it's not the person, it's the decision of a particular component of our AI system. It means that this component, this classifier, is pretty certain that the decision is produced is correct. Then the certainty factors theory is mainly based on two functions. One function, the first one, measures the belief, and the second function measures the disbelief. Okay, and you can see the equations on this slide. So the measure of belief is 1 if probability of a hypothesis is 1. Okay, we are pretty certain this is true. We are absolutely certain, so obviously the belief is 1. In any other case, the measure of belief is given by the relation that you see on the slide. Okay, it's a simple calculation. It's not very difficult to produce because it just by an equation. It takes the highest value, 1, if the probability of the hypothesis is 0. Okay, and then you can see in the formula it takes into account the minimum and produce a simple calculation. As you understand, we need the prior probability of hypothesis H being true, the probability that hypothesis H is true given evidence E. These are necessary in order to perform this kind of calculations. The values of the measures of belief and disbelief are in the range of 0 and 1. And the strength depends really on the belief or disbelief that we have in the hypothesis and on the evidence that we observe. Then what the system will have to do is to calculate the total strength of belief or disbelief in a hypothesis. So these two metrics, belief and disbelief, are calculated independently, and then all the data are put into this kind of equation to calculate the total strength of belief or disbelief in a particular hypothesis. And this is the CF, the certainty factor that the system is going to use. I have a simple example here. Let's consider an AI system that uses rules for reasoning, like simple rules of that form. If A is X, then B is Y. There is no absolute certainty that this rule holds. And let's suppose that we observe some kind of evidence. And the evidence that we have here is represented by the rule if A is X, then B is Y with certainty 0.7. B is Z with certainty 0.2. Okay, so there are two alternatives basically for B, and each one has a different degree of certainty, 0.77 and 0.2. So the certainty factor assigned by a rule is propagated through the reasoning chain. I talked about reasoning chains in last week, how the output, the result of one rule may trigger another rule, which also gradually causes a chain of inferencing and leads to the final decision of the whole knowledge-based system, for example. So it's the same thing here. We're going to use the information to calculate the certainty of hypothesis H when evidence E is available. And this is given by this simple calculation. It's the certainty of E times the certainty factor of the rule. Okay, so if sky is clear, then the forecast is sunny with certainty 0.8. Let's assume that's the rule that we have. And the current certainty factor of sky is clear. We have some evidence that the sky is clear, and the evidence is associated with some certainty degree, and the degree is 0.5 in this case. Then to calculate the output of this rule, we need to do this simple calculation. We multiply 0.5 times 0.8, which gives you 0.4, and this result can be interpreted as it may be sunny. Okay. This is how we are going to calculate the output of this rule, okay, given the evidence that we currently have. You can use this idea and you can produce complex rules, like in this case, which are more practical, because in applications usually you have conjunctive rules like the schemes like the one you see here. If evidence E1 and if evidence E2 and then hypothesis H with some certainty given represented by the value of the certainty factor you have assigned to the rule. Okay. How can we do the processing? It's very simple with certainty factors. So the certainty factor of H, of hypothesis H, when evidence is E1 and E2 and E3 and En is given by the minimum, as you can see on the slide. So we take the minimum of all these certainty factors for each piece of evidence, and this is multiplied with the certainty factor of the rule. Just a simple example to show you how it works. If sky is clear and the forecast is sunny, then the action is wear sunglasses with certainty 0.8. So let's say that we have collected some kind of evidence and that tells us that the certainty of sky is clear is 0.9. And the certainty of the forecast of sunny is 0.7. Then the output will be produced by this calculation, the minimum of 0.9 and 0.7, which is obviously 0.7, and this is multiplied with 0.8, which gives you 0.56. So the certainty of this rule at the end, the outcome is 0.56, and this can be used to trigger other rules in your system. If we use disjunctive rules, we have to take into account different, again, pieces of evidence, but the rules, the if parts are connected through the and or, then certainty factors theory does the calculation using a completely different operation. Okay, so the operation is not the minimum anymore, is the maximum. So we're going to calculate the maximum between the certainty factors of the different pieces of evidence that we have, and the outcome is multiplied with the certainty factor of the rule. If I go again through a similar kind of rule, if sky is overcast or the forecast is rain, then the action is take an umbrella with certainty 0.9. Okay. So let's say that the certainty of sky is overcast is 0.6. According to the output of another rule or the kind of evidence that the system currently receives, the data that the system receives. So sky is overcast is 0.6. The certainty of forecast of rain is 0.8. Then we are calculating the maximum between the two values. It will give us 0.8. We multiply with 0.9, which means that the result of this rule is going to be 0.72. Okay. The calculations are very simple with this kind of approach. It's one of the advantages. And the simple operations that have been defined. Someone could say that, look, in real world applications, sometimes things are not straightforward. So, for example, I have a case here where the same consequence, the same action is obtained as a result of the examination of two or more rules. So what is going to happen here, for example? Let's say that the AI system uses these two rules. Rule 1, if A is X, then C is Z with certainty 0.8. And then you have another rule which says if B is Y, completely different piece of evidence. Okay, then C, oops, it affects this rule again. It triggers the same kind of action, C. But it says that C is Z with a different degree of certainty, 0.6. Okay, so both rules, the if part is completely different. Okay, that's important. It means that they get information from different facts or different pieces of evidence. They receive different pieces of evidence, but the then part, the action part, the conclusion, affects C, but according to different certainty. Okay, so the C, the concept C, the object C, gets the value Z in both rules, but with different certainty. Fortunately, certainty factors theory has proposes a solution to this kind of problem, how we're going to deal with this kind of situation. It's based on common sense. Okay. Okay, what common sense says? Normally, we would say that, look, if two pieces of evidence from two different, variables, sensors, support the same hypothesis, then maybe the confidence in this hypothesis should increase. Okay, it makes this assumption much stronger, isn't it? It makes sense. So that's the idea. But with certainty factor theory, we have very specific equations again that we need to follow in order to produce the final result, the final value. And these are the equations. They take into account the confidence in hypothesis H established by rule 1, the confidence in hypothesis H established by rule 2. They also use the absolute magnitudes of certainty 1 and certainty 2, as you can see in the equations. So it doesn't matter whether it's positive or negative because we use the absolute. Okay, it was always going to be positive. But as you can see, the formula takes different, proposes just different relations depending on whether the certainty factors are positive or negative. So first, if both are positive, you use the first equation. If both of them are negative, you have to use the part in the middle. Sorry, not both of them. If one of them is negative, you use the part in the middle, and if both of them are negative, then it's the last equation that you have to follow. Okay. In any case, numbers are simple. There are values between 0 and 1, and you can easily do this kind of calculations. The certainty factors theory, it's an interesting practical alternative to Bayesian reasoning. As I said, it's heuristic. Basically, researchers have proposed specific operations. It's not mathematically pure. It doesn't have the strong mathematical basis that Bayesian theory has, but it has been used, and it works well in situations where the assumptions of the Bayesian method do not apply. As I said, one of the assumptions is that we have conditional independence among the different evidences that we have. So if this assumption does not hold, we have a valid reason that this assumption is not true, then certainty factors theory is an interesting alternative. Okay, and another situation that perhaps Bayesian method does not work very well is if we are lacking information about the probabilities or we don't have enough data. Because if you have a lot of data, you can use this data, calculate some statistics, averages, variance, and you can use the information to find these probabilities that you need in order to train Bayesian networks, or even create these simple tables of probability values that I used in my examples. Okay, but if you don't have the data, what are you going to do? Okay, perhaps you have a small data set, or you just have some people who are familiar with this kind of situation, and they can give you their perceptions, their beliefs about the different events and the different actions that you can take. Okay, so in these kind of circumstances, certainty factors theory, although perhaps it's more subjective, since it's based on humans giving you their beliefs, it's an interesting alternative. Okay. So let's see how are going to work when we use fuzzy logic. Okay, certainty factors, it's not a new theory. It was proposed in 80s and 90s. Bayesian reasoning is obviously much older, based on probability theory. They have both been applied extensively in the design of intelligent systems. Fuzzy logic is more recent. The name, it doesn't inspire a lot of confidence, I would say, but because of the use of the term fuzzy. Okay, so I have one video actually on Moodle. I hope you had a chance to go through it. It's the interview with Lotfi Zadeh, who proposed the theory, and he explains the problems that he had initially, because people were not very willing to use the term fuzzy. Fuzzy has a negative meaning, and when you are talking about logic that is fuzzy, it does not inspire a lot of confidence, as I said. However, fuzzy logic is not abstract at all. It has a very strong mathematical theory behind it, which is still under development, and actually very specific, very well formulated operations and theorems about reaching convergence and conclusions, making conclusions, dealing with imprecision, dealing with conflicts. So it's very, very well defined. It's not fuzzy at all, actually, despite the strange name. So it was proposed in 1965 by Lotfi Zadeh, as I said, and you can click in the slides, in the link, it goes to the video that talks about Zadeh. He proposed the theory in his famous paper, Fuzzy Sets. It was published in 1965. And Zadeh describes a formal system of mathematical logic. Okay, so it's not fuzzy at all, it's not heuristic. It's a complete set of logic which is based on mathematics, and introduce the concepts and explain how we can convert natural language terms into intervals and assign degrees of membership into the objects or numbers that belong to these intervals. Okay. Someone could say that, look, this idea, it's not new. It's true. It's based on the concept that something, an object or a concept or even a number, can be associated with different degrees of membership into a particular kind of class or group or concept. This is a type of multi-valued logic. It was introduced in the 30s by a Polish philosopher, Jan Lukasiewicz. So it's different from the classical logic. The classical logic operates, it's Boolean. You have only two values. Something can be true or false. Okay. So Lukasiewicz introduced a kind of logic that extends the range of truth values to the real numbers. So you don't have a truth table where numbers are either 0 or 1. You can have a truth table where numbers are between 0 and 1. Okay. So you can have, for example, the possibility that a man with height 181 centimeters is tall, and this is represented by a number which is 0.86. Okay. And we say that it is likely that the man is tall. This is how we could interpret this kind of number in this context. Okay, this is particularly useful because it allows you, when it comes to making decisions with machines, to follow an approach which is called inexact reasoning or approximate reasoning. Okay, which is completely different. It allows the machine to make decision even when there is uncertainty about the data that it receives. There is missing information. Still, the machine is able to perform approximate reasoning. This, as we understand, has very important implications. This is something that humans naturally do. In many occasions, we don't have the full information, but based on experiences that we have, we are able to make decisions. Okay, so it's very important for systems to design machines that will be able to make decisions based on imprecision. So to summarize, fuzzy logic is a set of mathematical principles about knowledge representation based on degrees of membership. Okay, it's multi-valued. So we are dealing with degrees of membership and degrees of truth. Okay, something, just to take it, to stretch it, can be completely false, can be false, sorry, not completely, false to some degree and true to some other degree. Okay, so there is no black and white. Okay. I have on this slide some examples, links. You can have a look on these videos about different kind of fuzzy logic applications. Okay, so fuzzy logic is used a lot in different kind of products that we use nowadays. Most of the cameras, Canon, SLR, I will talk about the first Canon next week, where the chip, the fuzzy logic processor was introduced. It is used for autofocus. Okay, so if you use a digital camera like Samsung or Canon, and you use the autofocus facility, it's based on fuzzy logic. Fuzzy logic is also used in other kind of in other appliances, even in cars. ABS control in cars, it's based on fuzzy. It was one of the first applications of fuzzy logic. In most of these cases, especially when it comes to automotive applications, you are not going to find this information in the manual. So because of the use of the term fuzzy, people in marketing were not very happy to put the term, to write it down, in brochures and manuals. Some systems, some appliances, they instead of saying fuzzy, they use terms like smart system or the intelligent application. Again, they use the term intelligence, they use even the term AI. They don't afraid to use the term AI, but they are afraid to use the term fuzzy. Okay, because they believe that it's going to influence the confidence of the customer. Okay. So in these examples, you can see different kind of applications. There are videos online on YouTube. An very interesting article here in Wikipedia about one of the first applications of fuzzy logic to control the brakes of an automatic train, the Sendai subway in Japan. That was developed by Hitachi, one of the first applications of fuzzy logic in large scale in the real world. So let me introduce you now to the concept of fuzzy set, which is very important to understand fuzzy logic. Normally, we are talking about crisp sets, and in crisp sets, we say that things either belong or do not belong to the set. Okay, normally. Okay, but in fuzzy things are slightly different. So in a fuzzy set, an element belongs to the set with a degree of membership. So each element is associated with a degree of membership. And I have this simple example here about the set of adults. So if we say someone is an adult, all people who are over 18 years old, they're adults. That's, a very crisp definition, very clear cut. It follows the standard logical approach. Okay, so if you are 18 and over, you belong to the set adults. Okay, and I can try to represent that graphically. So you have this sharp boundary which says that if you are below 18, if you are 17 and I don't know, 0.99, then you are a non-adult. You belong to the set of non-adults. If you are 18, you are 0.0, you are an adult. Okay. If we go to fuzzy, if we want to represent this kind of concept with fuzzy sets, then you see that the situation is slightly different. We have degrees of membership. So you have this, it's not a crisp boundary. There is this linear part. You have this, what the so-called graceful transition range, where numbers go between 0 and 1. So, of course, if you are more than 19, definitely you are an adult with membership degree 1. That's why you observe this flat region in the curve. But if you are 18, then you may be adult and non-adult at the same time, according to this theory. Okay, you are an adult to a degree of I don't know 0.6, and non-adult the degree of 0.4. This is what fuzzy logic will tell you. And fuzzy logic theory has very clearly defined operations which apply on fuzzy sets. Like in normal sets, we have operations like the union and the intersection. The same kind of operations are defined for fuzzy sets, but they have been defined in a very specific way. So in crisp sets, if you have two sets, like in my example here, my simple example, 1, 2, 3, and you are going to try to calculate the intersection with another set, 3, 4, 5, then we know that from set theory that only the element that is common to both sets will survive, and that's the element 3. So we have a new set which contains just one element, it's number 3. In fuzzy sets, the situation is completely different. So you can have, you can deal with situations like my statement here, which is completely fuzzy. Tom is tall and average. Okay, so we refer into a person and we say that, look, this person is both tall and average at the same time. Okay, this crazy scenario can be dealt with fuzzy logic. It's perfectly normal in terms of fuzzy logic. So you have two fuzzy sets, one about tall and one about average. And let's say that we have the fuzzy set tall man, which is defined as you see in the slide. And each one of these heights, 165 centimeters, 175 centimeters, 180 centimeters, you see it's associated with a number, 0, between 0 and 1. Some are 0, others are 0.25, 0.5. There is also 1. These are the membership degrees. So for each one of the elements of this set, the elements of the set are possible heights. Each element is associated with a degree of membership. And that produces a kind of fuzzy set. This particular representation is called discrete fuzzy set. You can have continuous fuzzy sets as well. I will give some examples later. So this is a discrete fuzzy set. It contains a clear set of members. These are the particular values that you see, 165, 167, 180, etc. And each one of these values is associated with a degree of membership, participation to the particular set, the set of tall men. We do the same for the set of average men. And then what fuzzy logic says is, you want to calculate the intersection, just calculate the minimum between the degrees of membership of each of the elements. So you take one of the elements, 165, for example. Both degrees are 0, so the minimum is 0. No problem. And let's pick another one. yes, 180 centimeters. So 180 centimeters has a membership degree of 0 in the set of tall men, and a membership degree of 0.5 in the set of average men. What's the minimum? 0. Okay. So in the intersection, the fuzzy set, which is now the result of the intersection operation of these two fuzzy sets, as you can see, associate the value of 0 with the element 180. Okay, so that's the whole idea. We produce another fuzzy set which represents the intersection of two fuzzy sets. Okay, and the elements of the new fuzzy set get the minimum degree of membership of from the other two sets. Okay, it's a very simple calculation, and this is how intersection is defined in fuzzy sets. People have also defined the union operation. A union in classical sets, it means that you merge the two sets together, so you have a bigger set, larger number of elements. Okay. In fuzzy logic, it's not exactly the same. So as you can see, we have a statement, which is another example of typical fuzzy logic. Tom is tall or average. No problem at all. We can easily deal with this kind of situation here with fuzzy. So you have the two sets, tall men and average men, and then the calculation of intersection is by taking the maximum of the degrees of memberships for each individual element. So you have the fuzzy set contains the same exactly number of elements as before, but the degrees of membership depends on the maximum operation. So for example, we had for 190, 1 in the set tall men and 0 in the set average men. Since we are taking the maximum in the intersection, in the union, we're going to have 1, the maximum value. Okay, so this is how we work. We create another fuzzy set. This is again a discrete fuzzy set in this example, where you have discrete elements that represent heights, and each element is associated with a degree of membership, a number between 0 and 1. Okay. I represent these operations graphically here by using continuous fuzzy sets. Okay. There are different types of continuous fuzzy sets. Triangular fuzzy sets, like the ones I have here. You can see A and B are represented by triangles. There are two different fuzzy sets represented by functions that take this triangular form. There are other popular types of membership functions used in fuzzy logic. You can have, for example, Gaussian fuzzy sets. They will look like Gaussian probabilities, okay? The well-known bell-shaped distribution. But in this case, it's not going to be a probability distribution. It will be a fuzzy set. Or we can use trapezoid fuzzy sets, trapezoid geometrical shapes, okay? Another interesting thing, I will talk more about that next week in the design of fuzzy systems, is that we can combine different types of fuzzy sets, different shapes to represent variables. So if you have one variable, speed, for example, you can represent different elements, terms of that variable using different types of fuzzy sets. You can combine triangular fuzzy sets and trapezoid fuzzy sets, for example. It's quite interesting. So graphically, as you can see, the intersection is just a smaller fuzzy set. As you can see in the figure, it's the overlap area between these two shapes. The union is going to give you something bigger. So we merge the two fuzzy sets and we produce another kind of shape, which is bigger. It contains elements of both sets. Okay. And this brings me to the notion of linguistic variable. Okay, well, we use variables a lot in our programs. I suppose you are very familiar with the concept. Here you have to understand that you need to stress a bit your definition of variable. Okay, this is a fuzzy variable. It's called fuzzy variable or linguistic variable. That's the terms used in fuzzy logic. When Zadeh introduced the concept, he used the term linguistic variable. Nowadays, I think most people are going to use the term fuzzy variable. So a fuzzy variable, like a normal variable, can take different values. But the values that a fuzzy variable takes are represented by fuzzy sets. So if I take the variable speed, the variable speed in the real world can take values in the range of 0 to 200 miles per hour. Okay. In fuzzy logic, the linguistic variable speed, it will take linguistic values like very slow, slow, medium, fast, very fast. Okay. Each one of these linguistic values, it's a fuzzy set. It's not one number, it's a fuzzy set. It's a set of numbers participating in this fuzzy set with different degrees of membership. Okay. And the whole range of possible real values that the fuzzy variable can take, okay, it represents the universe of discourse of that variable. So if in the real world, the variable speed, because let's say we are measuring the speed of a car, okay, we want to represent the speed of a car with as a fuzzy variable. So speed can take values between 0 and 200 miles per hour. The universe of discourse of the linguistic variable speed is from 0 to 200, okay? That's the universe of discourse. This is the range of all possible values that this variable can take in the real world, okay? On this universe of discourse, we define fuzzy values, fuzzy sets about very slow speed, medium speed, fast speed, very fast speed, okay? How many values? How many linguistic values? It depends on the resolution that we want to use, how precisely we want to cover this fuzzy variable, okay? And someone could say, all right, let's use, 5, 6, 7, 10, increase the resolution. Yes, obviously, you increase the resolution, it means that you increase the precision. But this has an implications on the design of your system. So it increases the complexity of the system, the complexity of the calculations that your system is going to have. And it's quite interesting that in applications, usually you don't have to do these kind of tricks. 3 terms or between 3, 5, or maximum 7 work very well. Actually, this is one of the advantages that this form of knowledge representation offers, that you can deal with imprecision. You can create a system that has 3 values, slow, medium, fast, let's say, and design the fuzzy sets, and your system will be able to perform reasonably well, although it's based on completely precise information, because there is this process of approximate reasoning. There are certain mechanisms that fuzzy logic uses to process the information that is represented by the fuzzy sets. Even cases where there is conflict between the rules in the system can be dealt with fuzzy logic. Another interesting thing is this concept of hedges, which allows us to modify the shape of fuzzy sets. So in real life, we use terms like very, more, quite, less, slightly, likely, very likely. Okay, these are terms that we use when we speak. We are very confident. Okay, what does that mean? Okay, in fuzzy logic, you can deal that. We can quantify these terms. It's quite interesting. For example, let's see here this slide where I have 3 fuzzy sets for one linguistic variable. So I have the linguistic variable, the fuzzy variable height. What does it mean? It's represented by 3 values: fuzzy sets, short, average, and tall. So it basically says that, look, everyone who is over 190 centimeters is tall, and the degree of membership is 1. But if you are between 180 and 190, then you can be tall and average at the same time, according to the different degrees of membership. So someone who is 185 may be 0.5 tall. Okay, and 0 membership in the fuzzy set average. Okay, according to this representation. Someone who is 182 centimeters. 182 falls inside in the interval between 180 and 185 you see in the figure, which means that this person belongs to 2 fuzzy sets. The fuzzy set tall to a degree of membership of 0.25, and to the fuzzy set average with membership degree 0.25. according to fuzzy logic, there is no problem. We can represent this kind of concepts. And you see how the modifiers, the hedges, alter the shape of fuzzy sets. So if something is very short, you see the change in the slope of the fuzzy set, okay, for very tall and very short, okay. It will bring this kind of change. Someone could say, what are you doing? You are arbitrarily changing the shapes of fuzzy sets. No, it doesn't work like that. This is because, as I said, there is a very specific mathematical theory behind fuzzy logic. So even words like very, more or less, extremely, slightly, likely has been precisely defined mathematically in fuzzy logic. So for example, you can see here what very means. Very is the square of the membership degree. So if you have a fuzzy set, you have membership degrees of the elements in the particular fuzzy set. If you apply the operator very, it means that the membership degree will change. You now use the degree to the power of 2. Okay, if you want to represent things which are more or less true, then you have to use the square root. Okay, so more or less is the square root of the membership degree. If something takes extreme values, it's the membership degree to the power of 3. If something is slightly modified, has slightly changed, then according to fuzzy logic, is the membership degree to the power of 1.7. Okay, this is how it has been defined. So it's very precise, not fuzzy at all, as you can see, despite the use of fuzzy in the definition of the theory. So for example, I have a simple example here to show you how it works. If Tom has membership 0.86 in the fuzzy set tall man, he will have a membership of 0.86 to the power of 2 in the set of very tall men, and a membership degree of 0.92 in the set of more or less tall men. Okay, all these things can be managed by fuzzy logic in a very clear way. So in real application, of course, okay, one way would be, to have a panel of experts or, domain knowledge experts who define the fuzzy sets. And this is done indeed in several cases, like in many of the applications that fuzzy logic is used, like in cameras, washing machines, air conditioning units. These companies have designing, cameras, video cameras, air conditioning units, devices for many years, so they have knowledge, extensive knowledge of, and they have done user studies, and they know exactly what users expect. So they can use this kind of information to initialize fuzzy sets and define the fuzzy terms. I have an example here based on simple literature, okay? Reading speed. So I searched the literature and I found psychologists have done a lot of experiments about how quickly people read, okay? And they have found out that on average, the average reading time per 100 words ranges between 15 seconds to 65 seconds. Okay, so the universe of discourse of users' reading speed in terms of fuzzy logic would be between 15 to 65. Okay, and then on this universe of discourse, you can define fuzzy sets. And as I said, the simplest way to start would be to say, look, I have just 3 fuzzy terms: slow, medium, fast. So I can use triangular fuzzy sets and design 3 fuzzy sets on this universe of discourse. And since the range is between 15 and 65, and our psychologists, researchers have found that on average it's 35, then it's very easy to make the assumption and say that, look, okay, so medium, the fuzzy set medium is centered around 35 seconds. Okay, so this is where the center of my triangle is going to be. 35 seconds, it's going to have a membership degree of 1. And then it's a triangle, and you can use the overlap between the triangles and design the fuzzy sets that will represent users' reading speed, for example. Okay. We can extend the concept to cover the rules, the concept of rules. In this case, the rules are called fuzzy rules, and they don't deal with variables. They take into account fuzzy variables. Okay. So a fuzzy rule in our case would say that, for example, if we take the scenario, someone burning calories by doing some kind of exercise at home using a bicycle, a bike. So the fuzzy rules in our case would say if speed is high and load is high, then the person burns calories fast, very fast, actually. If speed is moderate and load is high, then you burn calories fast. Okay, these are two rules which are represented in terms of fuzzy. The variable is speed and load. The action, the decision is to burn, the name of the variable, and the values are fuzzy. It's high, moderate, very fast, fast. These are represented by fuzzy sets in our case. Okay. So fuzzy rules will relate fuzzy sets, and in a fuzzy system, like in normal knowledge-based system, we have all these rules firing, but in fuzzy logic, they all fire to some extent. They fire partially. Okay. If the if part, when the if part of the rule is true to some degree, okay, the rule is triggered and it produces an action depending on the then part, which is again true to some degree. Okay, that's how it works. Next week, I'm going to talk more about how we use these ideas to build fuzzy systems. Okay, so I will start by explaining how we start by specifying the problem and identify the variables that we want to use. Variables most of the time come from sensors, from the environment. Usually they measure different kinds of things. These are our variables. And then we have to define the fuzzy sets for these variables. Because the fuzzy sets represent the values that these variables will take. Then somehow we would have to decide on the rules that we are going to use. We elicit the rules from domain experts, or we use data and we do some analysis, statistical analysis of the data to identify some information to use to produce rules. We produce the rules, we encode the rules in our rule base, and we have very specific operators to do the processing, which I'm going to explain in detail next week. And then what happens is that all these rules fire partially. There are specific operators to combine the outputs of all these rules and produce a decision. We evaluate the performance, and then it's possible to tune the fuzzy system, as we say. Tuning is done by altering the shapes of fuzzy sets or altering the form the form that these specific operators take, or even by doing some kind of cleaning of the rule base. What I presented today is in the book. You have to go to chapters 3 and 4. They make an introduction to the fuzzy logic. They also cover certainty factors theory and probability. That's the book I'm using. Ned Nevisky's Artificial Intelligence is the core book text, the core text of this module. I'm using the second edition. Currently, I think the third or the fourth edition is available. You can find very cheap the second edition on eBay for £3-4. I don't know, maybe it's already available online if you Google it, because there is a new edition. So maybe the second edition is already free somewhere online. You may also find useful these online articles. There are 2 tutorials about fuzzy logic that I have on this slide. And if you want to, it would be useful if you want to prepare yourself for next week. So next week, I will continue with fuzzy logic, and I will explain how we can design. We use these basic principles I presented today to design fuzzy systems, and how fuzzy logic can be used in fuzzy clustering. Fuzzy clustering is now standard algorithm in many packages like SPSS. So SPSS has fuzzy clustering. It's not, considered as a second-class method anymore. It has several advantages. It has been incorporated in several packages. And again, for next week, chapters 3 and 4 are relevant, and I have a link to an some online material, a tutorial on clustering algorithms. It's a very nice tutorial about clustering in general. The link points to the material which describe a particular method. It's called fuzzy C-means algorithm. A well-known crisp clustering technique is K-means. So this is the fuzzified version of the K-means algorithm. All right, for those of you who want to prepare for the following week. Okay, so I'll stop my recording here, and I will prepare another video for next week's lecture. Bye for now.